Now, let's say, like other variants of this first order model are the following. Okay, so please note that, like what we saw was this was to begin with, like this is what to say, one parameter model. Okay, like so this one, I don't know where I can write. Okay, let me write here. This was a one parameter model. Okay, in many textbooks you will see one parameter process. Okay, as I told you, like in systems theory, like there are a lot of chemical engineers also who work, like they will say first order process. Okay, that's what this is, right? So essentially, I'm just using a term which we are what to say, more accustomed to, which is of systems. Okay, so this is a one parameter model. Why? Because you give me capital T, I know the model, right? The transfer function has only one parameter, 1 by capital Ts plus 1. So let's say you give me the value of capital T, I'm done, right? I know the system model. Okay, that's why we call it as a one parameter model. Okay, now are there any other variants, okay, of this model? So let's look at this. So another variant is this t dy dt plus y of t is equal to b u of t. Okay, b is some real number. Okay, of course b not equal to 1, right? So because obviously b is 1, we end up with the same case as before, right? So what will be the plant transfer function in this case? Correct? Please repeat the same exercise. Okay, apply Laplace transform on both sides, take initial conditions to be 0, and you will see that the plant transfer function is b divided by capital Ts plus 1. The values of n and m remain the same. N is 1, m is 0. The pole is still at minus 1 over capital T. Okay, there is no difference or change in those aspects, right? But what changes now? So let's say we get the unit step response. Okay, now unit step response means u of s is going to be equal to 1 divided by s, right? So this implies that y of s is going to be equal to p of s times u of s, which is going to be equal to b divided by s times ts plus 1. So what will be y of t? Pretty straightforward, right? So we already know the answer of what happens when we have 1 divided by s times ts plus 1. So the y of t is just going to be b multiplied by e power minus t by capital T. So the only difference we get is that the steady state output is now b rather than 1. Okay, that is the change which comes, right? So if you plot y of t and t, right? So the point I am trying to make is that like the steady state values need not be 1 all the time. Okay, that's why I am doing these variants. Okay, so called variant. So the output will go from 0 and then like it will settle down to b. Okay, so that's what will happen. Okay, in this particular case. Clear? Okay. But there is another way in which you can find the steady state output. So suppose if you want to find the steady state value of the unit step response, you can also use the final value theorem. What does the final value theorem tell? Limit t tending to infinity y of t is going to be equal to limit s tending to 0 s times y of s, right? So if I use this expression, this is going to be limit s tending to 0 s times y of s is going to be this b divided by s times ts plus 1, right? So s and s cancels, you immediately see that I am going to get b. Okay, so this b for that reason is what is called as a steady state gain. what is the value when we reach steady state. Okay, steady state means like a t tending to infinity, what is the value to which the unit step response will go towards. Okay, so that's the steady state gain. In the previous variant of the first order system, we implicitly assume that the steady state gain was unity, but it need not be. That's what I am telling you, right? You can have steady state gains not being 1. That's perfectly fine. But everything else remains the same. The dynamic characteristics as far as time constant, settling time is still 4 times capital T, that remains the same. But now what will happen? You will see that if you substitute T equals capital T, Y of T will be B times 0.632. That's why the definition was 63.2% of the final value, not just 0.632. Okay, if you look at the definition. Similarly, if you calculate what is Y at T equals 4T, you will get 0.982 B. So the output would have reached 98.2% of the final value, which is B once again, right? Small b. Okay, so that's what is called by steady state gain. So immediately you see that this is a 2-parameter model. 2-parameter model or 2-parameter process. Okay, so this people will call first order model with non-unity steady state gain, right? So that's the variant. And a third variant which people can have, which essentially occurs in many practical processes. You will look at this variant even when you come to the lab. Okay, in many practical systems, you may have a system like this. Okay, so what this is of course TD is a real number which is positive. So TD is the delay time, right? So we have already encountered what was let me put it as time delay, right? So we have encountered what was time delay before, right? So that is, you give an input, output starts from 0 only after the interval of TD, right? So that's time delay, right? So immediately we know that the Planck transfer function is going to be what? Y of s divided by U of s. It's going to be B e power minus TDS divided by TS plus 1, right? How did we get this? B by TS plus 1 is for the previous one. Now you get an additional factor due to the time delay, which we have already calculated, right? When you take Laplace transform of U times T minus TD, you are going to get U of s times e power minus TDS. That's how we got this. Of course, you see that this makes the problem infinite dimensional, right? Because like e power minus TDS, you have a power series expansion. Then we looked at Paday's approximation and so on, right? So if I use the Paday's approximation, what will I get? I will have 2 minus TDS divided by TS plus 1 times 2 plus TDS, right? If I use the Paday's first order approximation, right? So if I use Paday's first order approximation, okay? So but the thing is, now this is a, how many parameters do we have? We have 3 parameters. So this becomes a 3-parameter model. Okay, so that's another variant. Okay, so this people will call as a first order system with a non-unity gain and time delay. Okay, some in chemical engineering references and all, you will see first order process plus time delay. Okay, so that's a term which they will use. Okay, so this is the model which is used, and this is the transfer function which comes about as a result. Okay, so you see that you have 3 parameters too. So once again, the dynamic characteristics remain the same. The time constant definition is the same. The steady state gain is once again B. Okay, only the difference is that now we have added a time delay factor. Okay, so that's the change that happens. Okay. Okay, is it clear? What is a first order system? Right? Okay. So now we go to second order systems. So once again, to recap the big picture, like as to why we are studying first order and second order system, the reason is that, like, by and large, when we want to talk about performance, right, we talk about the fact that we have the dominant dynamics, right, or dominant poles to be either 1 or 2. That is like what is close to the imaginary axis, right? That's why, you know, like when you want to specify performance, we look at either first order or second order systems. You know, like that's the motivation, you know, like behind looking at first order and second order systems for deriving performance parameters. Okay, so that is the big picture once again. So typically second order systems are motivated from vibration problems, you know, like so, and due to that reason their governing equation is written in a certain structure. Okay, we will see how it is written. Okay, so as I told you, you can have the general governing equation. That's why I wrote the general governing equation, right? A naught dny dtn plus a n dn minus 1 y dtn minus 1 and so on, right? That is the general structure, you know, like as far as we are concerned. We are considering specific structures motivated by some physical practical applications. Okay, like that's what we are doing. Okay, so the governing equation of second order systems is typically taken as the following. Okay, what is that? So typically what we do is that, like, we take it as d squared y dt squared plus 2 zeta omega n dy dt plus omega n squared y of t is equal to omega n squared u of t. Okay, so that's the general governing equation here. Okay, so once again, that's why I said, you know, it's typically taken to be this. Okay, so immediately you can see that n is equal to 2, right? So m for this particular case happens to be 0. You can also have m to be 1. Okay, you can also have a derivative of u on the right hand side, can happen. But as I told you, we would take it off to be of this particular structure. Okay, and we'd see what happens when we have n to be 1. Okay, that is, we have a term on the right hand side, what really happens to the system's response. Okay, that's something which we look at as we go along. Okay, so we can see that immediately. Of course, before we calculate the poles, you know, like the value zeta is what is called as the damping ratio. Okay, omega n is what is called as the natural frequency of the system. Okay, we would revisit these parameters, you know, like, and then I would ask you to define these parameters. Okay, like we are going to look at the physics behind these choices, right? So behind this choice of model, right? We'll look at them. But then, like for tomorrow's, or let's say for the next class, you know, I should say, you know, like, please figure out what is the definition of natural frequency and come. Okay, so a clear, crisp definition, okay, of what you mean by natural frequency. Okay, we discuss this as we go along, right? And it so happens that we will what to say, figure out later that for stability of the system, please remember, we can only talk about performance only if you have a stable system to begin with, right? Is it not? Right? It so happens that for stability of this class of systems, the sufficient condition is zeta being greater than 0, omega n being greater than 0. Okay, so that is the sufficient condition. Of course, in general, we will see that you know, like the system will be stable if zeta and omega n are real numbers of the same sign. Okay, but then, like, practically we want, essentially we are associating some physical meaning with these parameters zeta and omega n. So consequently, we take it to be positive, right? Damping ratio and natural frequency are going to be positive numbers. So zeta greater than 0, omega n greater than 0 is sufficient for me to give me stability. Okay, we will also later see that if you treat zeta and omega n as two parameters without associating any physics to them, we just need them to be of the same sign. Okay, even if they are both negative, we can have stability from a mathematical perspective. But then, like, physically we don't have frequencies being negative, right? So that's why we are taking this particular condition. Okay, this is only sufficient, please remember that. So now can you take the Laplace transform on both sides and calculate the system transfer function? So the Laplace of the second derivative is going to be s squared y of s minus s y0 minus y dot 0, right? So that's the Laplace transform of the second derivative. First derivative is going to be s times y of s minus y0. Then we are just going to have omega n squared times y of s. That's going to be equal to omega n squared times u of s, right? Now we apply 0 initial conditions. What would happen? We would get s squared plus 2 zeta omega n s plus omega n squared times y of s is going to be equal to omega n squared times u of s. So this implies that the Planck transfer function p of s is going to be equal to y of s divided by u of s. That's going to be equal to omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. Okay. So what are the poles of this transfer function? How do you get the poles? We solve the denominator polynomial equals 0. We solve s squared plus 2 zeta omega n s plus omega n squared equals 0, right? So the poles are going to be minus zeta omega n plus or minus omega n times square root of zeta squared minus 1, right? If you calculate the roots of this quadratic polynomial, right, this is what you will get. Am I correct? See, if you have a squared plus bs plus c equals 0, what are the roots? Minus b plus or minus square root of b squared minus 4ac, the whole thing by 2a, right? That's what I have done. Okay, so immediately you see that this is what we get. Am I correct? Right? Now, of course, it's a second order system, value of n is 2, obviously you get 2 poles, right? Now, what can you say about these nature of these poles? Immediately we can observe that the nature of the poles depend on the value of zeta, right? If zeta is between 0 and 1, what can I say about the poles? See, if zeta is less than 1 but greater than 0, zeta squared minus 1 is going to be negative. So that zeta squared minus 1, which is in the square root term, will be a negative number. So the poles will become complex conjugates, right? If zeta is exactly equal to 1, then what will happen? We will have repeating poles at minus omega n, right? If zeta is greater than 1, we are going to have 2 distinct real poles on the negative axis, negative real axis, okay? So those are 3 cases that we would look at, okay? Depending on the value of zeta, the location of the poles changes, and consequently the system behavior changes a lot, okay? So that's something which we are going to do in the next class. So we look at what are called underdamped, critically damped and overdamped systems, okay, depending on whether the value of zeta is less than 1, exactly equal to 1 or greater than 1 respectively, okay. So we look at what is the physical implication of those 3 cases, and then how do we do the analysis, okay. So that's something which we will do in the next class. But before that, please figure out the definitions of natural frequency and damping ratio, okay, and come.